Hey, welcome to AP Chemistry Unit 13, Chemical Equilibrium. So today we're going to talk about a new type of reaction called an equilibrium reaction. This is very related to Unit 12 where we talk about chemical kinetics. In Unit 12, we used a lot of math problems, a lot of formulas. There's a whole page of formulas I gave you. 13 is very similar. We're going to have to write a lot of expressions, use some formulas, solve a lot of math problems. Let's go ahead and get started. All right, so first we have chemical equilibrium. It is the state where the concentrations of all reactants and products remain constant with time. So to start talking about equilibrium, we first have to talk about what this reaction looks like. So a chemical equilibrium reaction gets a special symbol. It gets a right arrow and a left arrow, usually drawn on top of each other like this. Alternatively, you could draw like a full arrow top and bottom. It's another common way to draw it. But what these arrows mean is that there's a reaction going to the right, like normal, A being turned into B. Okay? So we have one reaction, A is turning into B. This is called the forward reaction. But the other arrow to the left means B is being turned into A as well. That's called the reverse reaction. This is more true to how a reaction would occur in real life, right? Not 100% of the products are being made from reactants or vice versa. In reality, they might favor one direction or the other, but both reactions are happening simultaneously. The forward reaction, A is being made into B, but the reverse reaction happens at the same time, B being made back into A. Chemical equilibrium is defined at the point where the forward and reverse equal out. So the amount A being turned into B is equal to the rate of B being turned into A. That's one definition of chemical equilibrium. Now there's a couple we're going to talk about. So a reaction doesn't stop at equilibrium. The rates of the forward and reverse reactions are equal. Okay? So during an equilibrium reaction, both reactions continue going, but they happen to be going at the exact same rate. So the forward reaction, the amount of B being made, is being held constant. The backwards reaction, the amount of A being made, is also held constant. And we're going to look at a couple graphs that kind of display this concept. So here, if I look at this graph, I have rate on the y-axis. That's how fast the reaction's happening. And if you look at my data on my graph here, I have Kf, that stands for the forward reaction. K is rate, F means forward, so that's the rate of the forward reaction. And then I also have the rate of the R reverse reaction. Okay? So I have the forward reaction, my reaction down here, N2O4, in equilibrium with two NO2s. Okay? As the system approaches equilibrium, both of these reactions are occurring. Over time on the x-axis, we want to see how these things change over time. So my rate of my forward reaction is some number. The number itself doesn't matter. But the rate of my reverse reaction is 0. So that means at the beginning, my initial conditions, my reaction of the reverse isn't going at all, which means you're starting with some reactant and 0 product. Okay? The rate of your forward reaction starts to slow down as you consume some of your reactant and turn it into product. When there's less reactant available to react, the rate of that reaction slows down. Meanwhile, though, you're making more product in the reaction, so the reverse reaction starts. And as you make more and more product, the speed of the reverse reaction increases. Eventually, they're going to meet an equilibrium, which is where the forward and reverse reaction are equal. At equilibrium now, I'm making kind of the same amount of product as I'm using. I'm creating the same amount of reactant as I'm using, therefore the rates stay constant. Another way to talk about this same sort of idea is with this graph. Looks similar, but this time I have concentration on my y-axis, so this is how much of each one I have over time. My concentration here, I have 0 of my NO2, which is my product, but I have some amount of my reactant. The reaction starts, and my amount of reactant starts to go down. My amount of product starts to go up. Well, eventually they're going to reach a point where these plateau. Okay? That's where equilibrium has been achieved, because now at this point in my reaction, my reactant and my product are both remaining constant. Now, this graph is different than the last one because notice they're not equal necessarily. Sometimes the forward reaction is creates more product than the reverse reaction, or vice versa. Like in this one, for example, I have 2 moles of NO2 being made for every 1 mole of N2O4 being consumed. So the concentrations don't have to be equal, but they do need to be unchanging. Okay. I have these 2 graphs next to each other here, which I also gave you on your notes. These are 2 different definitions of equilibrium. It is the point in time where the forward and reverse reaction are the same, or it's the point in time where the concentrations don't change. Those are 2 of the 3 definitions for equilibrium I'll give you. We have one more soon. Couple of technical definitions we have here. If the reaction favors the products within the chemical reaction, we say the equilibrium lies to the right. Products are on the right side of the arrow, so that's kind of what that means. We're going to talk about some reactions. The forward reaction is a lot more favorable, meaning it happens a lot faster, more frequently with a higher rate than the reverse. In that situation, we say the equilibrium lies to the right. It's going to make more products than it does reactants. Conversely, the reaction favors the reactants. You could say that the equilibrium position lies to the left. Okay. We haven't talked about any reactions like that so far, but we will. Okay. Past the definition, talking about the equilibrium constant now. So we have the following reaction at equilibrium. Okay. Yours may say something slightly different than this because I messed up, but that's okay. Your reaction here should say little a, big A, plus little b, big B. The little a is just talking about the coefficient. So if I have 2 A's or 3 A's, is in equilibrium with little c, big C, plus little d, big D. Okay, this is a general form reaction. So this is if I have any coefficient of reactant times whatever the reactant is, plus some coefficient times the reactant, I can write what we call the equilibrium constant. The first one we're going to talk about is K with a little c. Kc equals this expression. It looks complicated, but it's products over reactants. So on the numerator, you're going to have your products. You have C and you have D. We put it in brackets because we're interested in concentration. That's actually what the little c stands for, is concentration. So we put it in brackets because that's the molarity of that thing. So we have the molarity of our thing C raised to the power of C. Now this c is talking about the little c, the coefficient. We have it times the concentration of capital D raised to the lowercase d, which is talking about this d. So you put your products on top with your coefficients being your powers, divide by your reactants, products over reactants. Same thing here though, I have my A to my A power, B to my B power. A, B, C, and D are just whatever chemical species. You could have more than 2 on top and bottom, you can have less. The square brackets, remember, are the concentrations of those species at equilibrium. And then A, B, C, and D are the coefficients in the balanced equation. You might need to change your paper a little bit to match this, but you can leave it too, it doesn't really matter. Main thing here, Kc stands for equilibrium constant, and this is specifically for concentration, which we'll kind of talk about what that means. Let's write an equilibrium constant to practice it. For the reaction between hydrogen gas and oxygen gas to produce water vapor. Okay. So I'm going to try to write that reaction. I have hydrogen gas, which is H2, because it's diatomic, plus oxygen gas, which is O2, to produce water vapor. Okay. We're going to write the equilibrium arrow because we're writing an equilibrium constant. Water vapor is just water, H2O. Now I just need to make sure to balance this before I do my anything else. So I have 2 O's over here now to match those 2 O's. But now I have 4 H's, so I also need a 2 here. And we have our balanced reaction, hydrogen gas, oxygen gas, water vapor. I'm going to write my equilibrium constant, which is Kc. So Kc, we're going to start with the products. I'm going to put H2O in brackets. And I'm going to raise it to whatever coefficient I have, which is 2. I'm going to divide by my reactants. I'm going to start over here with H2, put it in brackets because I'm worried about its concentration. It has a 2 as well, so I'm going to raise it to the second power. And then O2 is last. No power there, so I just write it like that. And that's it. That's my equilibrium expression. If it gave me concentrations here, I could plug them all in and solve for K, which is our equilibrium constant. The equilibrium constant is really important. It gives you information about where your equilibrium lies, to the right or left. Think about it a little bit. If K is a really big number, say K was 1,000 or something, for example, okay? Think about where those numbers come from. It comes from this fraction, where you have products on top, reactants on the bottom. Another way to write 1,000 is just 1,000 over 1. If K is equal to 1,000, that kind of means you have 1,000 times more products than you do reactants. Opposite, if it's really small, like 0.001 or something like that, right? That's 1,000th, right? That's also the same as doing 1 divided by 1,000. In that case, you would have 1,000 times more reactants than you do products. A large K means you have a lot of products. The right favored equilibrium lies to the right, or it's a right favored reaction. Small numbers of K means the opposite. That's kind of what K is used for. Writing equilibrium constants is important, and it's an easy way to get a couple points on the AP exam on the FRQ section. Very commonly asked question. Okay, let's use that. Make sure to remember it's products over reactants, which might look a little bit weird, but you'll get used to it. You must also make sure to plug in final or equilibrium concentrations. What that means is these numbers, go back real quick to my DocCam. When I plug in something for this, I can only plug in my equilibrium concentrations into here. Okay. K is my equilibrium constant. It tells you what your reaction is like at equilibrium. So the only numbers I can plug in here are my equilibrium concentrations. My concentrations, once my reaction is settled down, and those aren't changing anymore. K is unitless. Okay. Couple things about the equilibrium expression. If the reaction is reversed, the reciprocal of the old K value is the new one. Let's start with just that piece of info. So I want to know the Kc of the reverse reaction. Well, if you reverse a reaction, say I reversed this reaction we were talking about, let's just flip it. I make 2H2O, 2H2 plus O2. If I write my equilibrium constant now, my products and reactants just swap sides. So when I write this, it's just going to be flipped. So the equilibrium constant of the reverse reaction is just 1 over the Kc of the forward reaction. If the balanced equation for a reaction is multiplied by a factor x, the new K value will be raised to that power x. So if I take this same expression, let's say I have this one. Say the K for this one is equal to 10 to make it simple. Let's get this one out of the way just to be clear which what I'm talking about. Let's say I'm going to multiply this whole thing by 2 to get 4 H2Os, 4 H2s, plus 2 O2s. I think the most obvious thing to do to K would be to double it as well. But remember, when you plug these in to Kc, you're taking the coefficients and instead turning them into exponents. So if you double all these exponents, you really need to square the K from the first one. So I multiplied everything by 2 here, raise it all to a factor of 2. So I'm going to take this and square it to get 100. The last little conclusion here is the value of K will remain constant regardless of the initial concentrations of the reactants and products. K does not care how much you start with of each thing. Your same equilibrium will be reached regardless. Okay? K only cares about the equilibrium concentrations of things. Let's do a couple of these examples using this concept. Okay, so calculate Kc for this reaction. 2HI is in equilibrium with H2 plus I2. I am going to write, when I write this down, all of the states of matter, because it is going to come into play, actually. Maybe not for this question, but for one down the road. Okay, this reaction is already balanced for me, which saves me some time. I want to go ahead and write Kc, the equilibrium expression for it. That's what I want to calculate at the end. Kc is products over reactants, so my two products, I have H2 and I have I2 over my reactants, I have HI. And there's two of those, so that's got a square. It's why it's important to make sure your reaction's balanced so you get the right exponents here. Well, that's my expression. These numbers are going to come from the rest of the problem. It says HI is 0.777 molarity, and it says specifically given that at equilibrium. So these are the equilibrium concentrations. It means I just plug them right into here. So H2's concentration is 0.233 according to the problem. I2 is 0.233 as well. HI, it says, is 0.777, but I have to remember to square that. I'm going to plug all this into my calculator, do these two times, divide by both of these, and I get my Kc for this one equal to 0.0899. If you're having some issues putting that into your calculator, make sure the denominator part's working out right. I'm sure you multiplied these fine. When you divide, make sure you're dividing by this number twice or dividing by it squared with parentheses just to be safe. Okay, so that's kind of our first problem. Given a reaction, given the equilibrium concentrations, I can solve for Kc. The next example, calculate Kc for this new reaction, but the reaction looks very similar to the old one. I now have, let's do it over here, 4HI gas in equilibrium with 2H2 gas and 2I2 gas. Given the Kc for the reaction, the previous example is 0.2. So just to simplify, I'm going to make the K over here, let's say it's equal to 0.12. It's really equal to this other number we found, but we're just going to keep the numbers a little bit simpler. K can change at different temperatures. So let's say that K happened to be this. Should probably fix that for consistency, but let's just go with it. If K is equal to 0.12 for this reaction, what is this reaction? Okay, well, first of all, it looks just like I doubled everything. So I'm going to call this one K1. I'm going to call this one K2. K2 is going to be K1 squared. Because we doubled all of these, we're going to square our answer. K2 is 0.12 squared, which is 0.0144. Okay, so I could also have solved for all of this if they gave me the equilibrium concentrations, but they didn't. So I'm going to manipulate the equilibrium concentration. I doubled everything, so I can use this relationship to find K2. Calculate Kc for this other reaction. I have H2 plus I2 in equilibrium with 2HI gas. Okay, this is just like this reaction, but it's inverted. I'm going to call this one K3. It's going to equal 1 divided by K1. We flip the reaction, which means we're going to flip products and reactants. So to get K3, it's just 1 over 0.12, which is 8.33. Okay, so that's how you manipulate or solve for K. And that's kind of what it means. We're going to talk about Kc and Kp. Kc is the version that involves concentrations. If your problem gives you concentrations of all your different things or molarities of them, you're going to solve for Kc. You can do that with aqueous solutions or with gases. We won't actually be able to do them with solids and liquids. We'll talk about why in a bit. There's also another type of equilibrium that involves pressures. So that's called Kp. It's only for gases though. For of reaction, so here's my general form. Little a again, little b, all those things again. I have a new equilibrium expression, this one with Kp. Now this works the exact same way. Products over reactants raised to the power. It just looks different. We have capital P, which just stands for pressure. So in this problem, I'll give you a pressure of all the different things in here, and you can find the equilibrium pressure. Okay, so Pc to the little c power, Pa to the little a power, Pb to the little b. The symbols are different, but you set it up the exact same way. So here's a reaction. I should mention, you can only do this with gases because gases have pressure, right? Solids don't. Liquids kind of do, but not in our class at all. Okay, so I want to write Kc and Kp of this reaction. So let's do that. All right, so Kc is with concentrations. So because it's concentrations, we're going to use the brackets to write it. I'm going to write NH3 in brackets and put my little 2 above. The bottom, I'll put my reactants. I have N2. That's just 1, so I'll just leave it like that. I have H2, and that one's raised to the third. That's my equilibrium expression with concentrations. Now to write Kp, it's the exact same thing. It just looks funny. That's the pressure of NH3. It's squared because there's a 2 in front of NH3, so I'll write it like that. Over the pressure of N2. Okay, that's just to the first, so I'll just leave it like that. I write it in parentheses, honestly, because I like how it looks. You don't have to. And then H2, which I'm going to write in parentheses because I need to raise that to the third. You do these in the exact same way. The only difference is in the problem, this gives you the pressures of things, so technically it's called Kp. This gives you the concentration, so technically it's called Kc. You will see both. Honestly, you could do it with just K without even like C or P, and it's totally fine. You're going to get the same answer. But just don't get freaked out when you see that. Okay, so on the next section here, we have homogeneous equilibria, which involve the same phase, meaning everything's a gas or everything's a liquid or everything's one phase. So like this top one, everything's a gas. Bottom ones, everything's aqueous. Okay, that's what we'll see the majority of the time. There we go. Opposite to that is heterogeneous equilibria. Involve more than one phase. So I have a solid in equilibrium with a solid and another gas. Now at the bottom I have a liquid in equilibrium with 2 gases. Okay. Curious, with homogeneous, you could say homogeneous. Heterogeneous, is there like a shortcut version of that word? Let's go. Not in English class. Let's continue. Okay. Heterogeneous equilibrium. I tried it. The position of heterogeneous equilibrium does not depend on the amounts of pure solids or liquids present. The concentration of pure liquids and solids are constant. So, you do not include solids, you do not include liquids in your equilibrium ever. Only gases and aqueous things. You can mix and match gases and aqueous just fine, but you do not include solids, do not include liquids in your equilibrium expressions. They don't matter. Doesn't matter how much of them you have. Writing this equilibrium expression here, the only one that's a gas is O2. So that's the only one that gets written. I ignore the KClO3, I ignore the KCl, and just write that. The equilibrium constant can give a lot of information about a reaction. It allows us to 1. Predict the tendency of a reaction to occur. 2. Say whether a set of concentrations represents a system in equilibrium. We'll talk more about what that means. We're going to talk about something called Q and compare that to K. And then 3. Predict the equilibrium condition that will be attained giving certain initial conditions. So if I start with different initial concentrations, how am I going to get to equilibrium? This is what I was mentioning too early before. The size of K. A value of K much larger than 1 means that at equilibrium, the reaction system will consist of mostly products. The equilibrium lies to the right, and another way to say that is the reaction goes essentially to completion. K is a ratio of products to reactants. If K is a very large number, you have significantly more products than you do reactants. Very small k is the opposite. It means that the system at equilibrium will consist of mostly reactants. The equilibrium position is far to the left. This actually means the reaction doesn't really occur to any significant extent. Only a little bit of my product would be turned, or my reactant would be turned into product. Again, a ratio of products to reactants, a really small number, means a big denominator, a lot of reactants. Sorry. It's important to pay attention to initial concentrations versus equilibrium concentrations. The initial concentrations of products and reactants can be used to determine which way the reaction will proceed. If the concentration of one of the products or reactants is 0, then the reaction will shift towards the direction of the missing component. We're going to get into some problems in a second, where I give you, say there's 2 reactants in a product, and I'm going to give you the concentrations of all of them. I'm going to tell you how much starting N2 and H2 and NH3 you have. If any of those numbers are 0, that means it's not possible for the reaction to occur using that reactant or product that has 0, because you can't have a negative amount of something. So a hint that we're going to talk about, and I think it'll make more sense in the context of the problem, is if you have 0 of something, the reaction has to go that direction. You can't possibly go the other. Okay. It makes it more difficult, though, when all of the concentrations of reactants and products are non-zero. Another way to say that is if you start with both products and reactants, you have to do some math to determine which way the reaction will go. The direction that the reaction will proceed to reach equilibrium must be determined. That's what we use the reaction quotient for, Q. The reaction quotient Q is used to predict which way the reaction will proceed. Q is identical to K. It's calculated using products and reactants, the same setup. But the main difference, K can only be used at equilibrium. But Q is when your system is not at equilibrium, when your reaction is just beginning, or in the middle of your reaction, or if you're testing to see if you're at equilibrium. We compare Q to K. We can check which way the reaction needs to go to finish. Calculating the reaction quotient is a way to check up where your reaction currently is and which way it's going to have to go, left or right, forward or reverse, to get to the equilibrium. Okay. 3 possibilities. If K is equal to Q, that means K is at equilibrium, Q is anywhere. If they're equal, that means the system is at equilibrium. That is the third definition of equilibrium we'll need. The system is at equilibrium when K equals Q. No shift will occur. Now, if K is less than Q, the system will shift to the left. If K is greater than Q, the system will shift to the right. A lot to kind of keep straight. Okay, let's try to break it down a little bit. Let's look at K versus Q. Let's start with K less than Q. I got to think about what this means. Okay. I need to think which way the reaction is going to go to finish. It says it shifts to the left, but I don't trust it. I want to calculate it. Q is products over reactants. But it's when it's not at equilibrium. So this is now, the now time. K is what my products over reactants will be once I reach equilibrium. I know I'm not there because K doesn't equal Q. So at EQ. Okay. So what this equilibrium means is Q is bigger than K. Q is too big. Okay. To make this number smaller, I need more reactants to make it equal K. Q is products over reactants. To make the number smaller, I need to decrease my numerator and increase my denominator. Okay. Doing either of those things, both of them will happen at the same time. But if I do either of those things, Q will get smaller. Eventually, Q will get small enough that it equals K. Well, let's think about it. I am losing products. I am gaining reactants. If I'm gaining reactants and losing products, the reaction's going left. So when Q is too big, I need to make more reactants and lose some products to get to my equilibrium. Shortcut though, easiest way to remember that. K less than Q. Write them in alphabetical order. K is before Q, so always start with K. That's how I remember it. This little equals or less than sign, imagine that's the top of an arrow, and you could draw like a little arrow like that. It points left. That's why you need to make sure you have it in the right alphabetical order. But that kind of gives you a hint. Finish the arrow. It tells you which way the reaction goes. Same thing here. If we do K greater than Q. If K is greater than Q, Q is too small. To make Q bigger, right, we need to make products bigger, make the numerator bigger, or make reactants smaller. To get more products, I need to go to the right, which will also use up my reactants. If K is bigger than Q, my reaction goes to the right. This is a very common question. I'm going to ask you this on your test for sure. Your AP exam will ask you about this as well. It's a really important concept. K versus Q. Q tells you the conditions now. K tells you what they need to be at equilibrium. Comparing them allows us to see which way we need to go to get there. All right, here we have a couple examples. K is 96.2, so it tells us K for the reaction A plus B equilibrium with C. We're going to use the reaction quotient to predict the direction to reach the direction of a reaction, to predict the direction of a reaction. We have three different cases here. We're going to start by writing out so A, B, and C. Okay, I already know what K is. It told me K is 96.2. So I'll just kind of keep that in mind. A, Q equals, it's going to be products over reactants. So my product is C. I have A. I have B. Well, for answer to part A, I'm just going to plug in the numbers it gives me. It says A with a little O on the outside, or 0 on the outside. That stands for initial concentration. So that's my initial amount of everything. So my C is 0.389 over 0.0933 is A. B is 0.123. Plug in everything and find Q. So I already did this. I'm just going to cheat. And my answer was 33.9 when I plugged that in. So now let's compare K and Q. Shortcut if you write it in alphabetical order. K, we said, is 96. Q is 33. K is greater than Q. Fill in the arrow. This reaction is going to go to the right. Let's try B. B, same Q, but just different numbers. So my C this time is 0.999. Okay, that means I have a little bit more product than I did last time. Okay, so Q is probably going to be higher. My A is 0.0233. My B is 0.0123. Plug this into my calculator, and this one's a large number. 3,000 something. 3486. Compare K and Q. Q's bigger this time. So Q's bigger, greater than. Okay. Draw my arrow. This reaction goes left. Okay. If a question asks you which way the reaction will proceed, you can use this little shortcut to help you. If the reaction says to justify why, though, that's when you need to talk about this. Let's do C. Q equals now. So my initial conditions are different. Let's see which way I need to go to get to equilibrium. 0.1067 over 0.0333 times 0.0333. Plug all that in. I get 96.2. K equals Q. So this reaction is already at equilibrium. And that's what Q is used for. Compare it to K, see which way you need to go. Q can be your initial concentrations. It can be your current concentrations. K is only your equilibrium concentrations once the reactions are equal. All right. Example, the equilibrium constant Kp equals 0.0041. So we're using Kp instead of Kc this time, but that just means our units will be pressure instead of molarity. Everything else is identical. For the reaction, it gives us a reaction. Make sure it's balanced. This one already is. It tells us the temperature, may or may not matter. Let's look. Find the equilibrium pressure of each compound. Okay. So I want to see how much COCl2, how much pressure of CO, how much pressure Cl2 all have. So what that means, of each compound in the system, if 0.124 atms, that's pressure, of COCl2 is allowed to reach equilibrium at this temperature. Okay, this question is getting into the meat of the harder equilibrium problems. When we do that, we want to keep all of our thoughts organized. We're going to do so with what we call an ICE table. So I'm going to go to my DocCam here, and I'm just going to put in all this information. I'm first just going to write my reaction. COCl2. Doesn't give me a state of matter, but it's a pressure, so I know it's a gas. Doesn't really matter then. Plus carbon monoxide plus chlorine. I'm going to write over here what we call an ICE table. I'm going to write the word ICE. I stands for initial. I'll put my initial concentrations of things here. C stands for change. I'll put the amount that changes there. E stands for equilibrium. My equilibrium concentrations there. In this problem, that's what I'm looking for. The equilibrium, not concentrations, but pressures. So my final answers will be here, here, and here for the three different compounds. All it tells me, my initial pressure of COCl2 is 0.124 atm. I assume then, based on the language, I start with none of this and none of this. First thing I need to do is think, which way will this reaction proceed? I could calculate Q. Compare it to K, because it gives me K. Kp is 0.0041. Okay. Or, well, I have none of this and none of this. At the beginning, the reaction won't be going left at all, because I don't have anything to make it. I don't have any ingredients to make it go left. Therefore, I know this reaction is going to proceed right. Okay, so my change here, my 0.124 atms of COCl2 is going to start being consumed. I don't know how much is being consumed, because I can't do this math in my head, so I'm just going to put minus x. Some amount's being consumed, and plus x for these two, because there's some amount is being made. I'm going to write my equilibrium concentrations of everything here. 0.124 minus x. Okay, so still don't know what it is, but that's the expression that represents what my answer will be. This one is just x. This one is just X as well. A lot of mystery in this problem. Well, let's go ahead and set up our KP. We know what the answer is. 0.0041 equals my products over reactants. My concentration of CO, concentration of Cl2 over CO, Cl2. Right? This is Kp. This is my equilibrium expression. I'm just going to plug in my variables here. This is X. This is X over 0.124 minus X. Okay. Now we just need to pull out our algebra skills, solve this equation, okay, and then plug in, solve it for X, and then we'll be able to figure out what these are, and then plug in to figure out that concentration as well. So let's get to simplifying. I'm going to cheat a little bit to save time. We'll go over this in class. We'll do some full examples to solve this to completion. But what I'm going to do is I'm just going to try to simplify this and get it into standard form. A squared plus B squared equals C squared. No, that's something different. Sorry. You'll see. Math's not my thing. Okay. I'm going to multiply this up there to get this on the right side, and I'm going to combine the two x's to get x squared. So I multiplied this, I moved it up here, multiplied the x's together to get x squared. Now I'm going to distribute this number to both of these terms. Get a really small number here, 5084 minus 0.0041x equals x squared. Okay. This is looking like a quadratic. I'm going to get all the numbers on one side, set it equal to 0. So I'm just going to add the numbers over here to the right to make more of them positive. 0 equals x squared plus 0.0041x minus 0.005084. Now to solve for x, I need to solve the quadratic formula because I don't think this factors very nicely. So I'm going to solve the quadratic formula. If you don't remember how to do that exactly, right, it's negative b plus or minus the square root of b squared minus 4ac all over 2a. A, b, and c correspond to the coefficients on this term as a, b, and c. Or you plug it into your calculator or Wolfram Alpha or something, and I get 2 answers. We'll run through this process, at least one together, but I'm just going to go to the answer to save you guys some time. I actually get 2 answers because it's plus or minus. So I get negative 0.025 or x equals 0.021. Okay. I'm going to just pull up just this so we can see the whole problem. All right, which of these is my right answer? Well, let's think about it. If this is the right answer, when I plug in for x, I'm going to have a negative amount of this carbon monoxide. Can't have a negative of something, so it's not the negative answer. X is 0.021. Okay, so that means that is 0.021 is my concentration of Cl and of Co, because they just equal x. And then this one, I just do the math, 0.124 minus 0.021. And what I get? Where is it going? 1 second. 0.103. So those are my 3 answers for my 3 concentrations. Bet you didn't think you're using the quadratic formula in this class. Okay. Here are the kind of the step-by-step guides to what we just did. Solving an equilibrium problem like the one we just did. I highly recommend using an ICE table. Setting everything together, it'll really help you figure out which pieces are missing. Sometimes you'll have to do what we just did and solve a whole equation. Sometimes it'll be pretty simple, but it's really hard to just look at all those numbers and know what to do. So here's the steps I would follow. Write the balanced equation for the reaction, if it's not given to you already. Number 2, write the equilibrium expression. Kc or Kp, write what it equals. List all the initial concentrations in the ICE table. Number 4, calculate Q and determine the direction of the shift of equilibrium, if necessary. In the last problem, I didn't have to calculate Q because I had 0 of something. The reaction always goes towards that. But if I have initial reactants and products, I'm going to calculate Q real quick, compare it to K, see which way the reaction is going to go. I'm going to need that for step 5. Subtract X from the side where the concentration or pressure is decreasing. Add X to the other side. 6. Substitute the equilibrium concentrations into the equilibrium expression. Solve for the unknown. Check your calculated equilibrium concentrations by making sure they give the correct value of K. That's what we just did. We didn't check our work, but it's probably good. But that's essentially what we just did to solve the problem. Let's try another one. We're going to set up an ICE table, see what we need to do, get the answer. This one's much faster. So I'm going to plug in all this information. I'm first going to write it down because there's a lot there. So the numbers here, I'm just going to copy them down for us here. Write down my reaction first. N2 plus H2. I have 3 of those. Make 2 NH3s. My favorite reaction. We have my ICE table. In the problem, it says it gives me initial concentrations of all 3 of these. My initial concentration of this is 0.25. H2 is 0.75. And H3 is 0. I really like seeing the 0. It will make our math easier, and it tells me which way the reaction's going. It has to be going this way because I don't have any of this to start with. So now I'm going to write the last thing in my reaction is equilibrium of NH3. It tells me the equilibrium amount of NH3, which is great. That's going to save me some work. My goal is to find the equilibrium constant Kc. If I want to go ahead and write the expression here, I can. It's going to be NH3 squared over N2 H2 cubed. Done that one a couple of times. I have my ICE table here. If it helps, you can draw some lines to help you kind of keep everything oriented. And now we're going to go ahead and solve. We know the reaction goes to the right, so I'm going to be producing some of this. Every reaction is going to make 2 NH3s. So to represent that, I need to keep these mole ratios in my mind. Instead of just saying X, I'm actually going to do 2X. Every reaction will make 2 NH3 molecules. Over here, I have N2. I'm going to lose one of those every reaction, so I'll say minus X. I'm going to lose 3 H2s, so I'll say minus 3X. Okay. Now this problem is easier, because if I look here at the NH3, I have the initial, the change, and the equilibrium. So I start with 0, I add 2X, and I get 0.48. Well, I can just solve for X then. X must be 0.24. Because 2 of them increases me by 0.48. So instead of solving all this mess, I can just use the information in my table to find X this time. So this one is losing X. Okay? So it's losing 0.24. It's left with only 0.01 as its equilibrium concentration. This one's losing 3X. So it's losing 3 times that is 0.72. It's only left with 0.03 molar concentration. So this time, without having to do all that complicated math, I was able to figure out my equilibrium concentrations, which now I can plug into this. Concentration of NH3 is 0.48. Square it over my concentration of N2 is 0.01. Concentration of H3 is 0.03, and I have to cube that. Plug all this in my calculator. What do I get? Really big number, 8.5 times 10 to the 5th, or 850,000. This K is a huge number, meaning products are heavily favored, which makes sense if we look at this reaction, right? I started with only reactants, but look, almost all of it turned into products. So this is a very product-favored reaction. Almost all of my reactants got consumed. Almost all of everything turned into a product. Okay. One more kind of long example. This is the last long one that we have in this lesson. Okay. All right. Again, we're going to get some really ugly math that I'm going to take a cheat on, and we'll talk about how to do it later. Determine the equilibrium concentrations of all substances in the reaction. Same reaction as before. Gives me initial concentrations of all three. Gives me the Kc of the reaction. This gives me almost identical information to the last one, except it didn't give me the equilibrium amount of NH3. So I'm getting one less piece of information, but it gives me everything else. Okay, so let's go ahead. I'm going to do the same as I did before. I'm going to write all this information into my ICE table. I'm going to write my reaction. I'm going to write the word ICE. My initial concentrations, N2 is 0.15. H2 is 0.10. And H3 is 0.05. This time it gives me Kc equals 1.5 times 10 to the fourth. Okay. I want to determine the equilibrium concentrations of all. So I'm going to see how much of this, this, and this I end up with. All right, so let's start to break it down. I need to see which way does this reaction go. Well, none of these are zero, so I have to do a little bit of math to figure that out. I got to find Q. Q is going to be products over reactants. It's going to be my NH3 squared over my N2 over H2 cubed, but it's with my initial concentrations. So I'm going to plug in my initial NH3 is 0.05 squared over N2 is 0.15, H2 is 0.1 cubed. I'm going to plug all this in, and I get 16.7 as Q. Let's compare K and Q to see which way the reaction will go. K is bigger than Q. Reaction goes to the right. Make sure this is in alphabetical order. K comes first, then you write Q, then you can use that little shortcut. All right. So this reaction goes to the right, which helps me get my signs right. I'm going to plus X, sorry, that's wrong. I'm going to minus X here. I'm going to minus 3X here. I'm going to plus 2X here. I don't have any hints about any of these, so I'm going to have to instead add what this is going to be. This is 0.05 plus 2x. This is 0.1 minus 3x. This is 0.15 minus x. I'm going to plug all of those into Kc, which is going to look identical to this, to Q. But I'm going to do it with these values. So Kc is 1.5 times 10 to the fourth equals 0.05 plus 2x squared over 0.15 minus x, 0.1 minus 3x cubed. That's an equation there. That's something a mathematician might like solving, but I do not. I'm going to type this into Wolfram Alpha, and it gives me two answers. Now, I'm going to give you some reasonable ones on your worksheet and stuff. I kind of made a mistake while planning this, and that's why we're cheating, and I don't want to waste all your time solving. I honestly, I can't solve this. I'd have to really think about it. But, yeah, we're going to cheat just to save time. There's two answers to this, just like before. Here they are. The internet's really a beautiful thing. I have to figure out which of these answers is good, though. Okay. One of these answers will make my answers nonsense. So let's start with this one. 0.15 minus x. Does that make either of these invalid? Actually, it does. 0.15 minus 0.15019 is going to make this a negative number. You can never have a negative amount of something. Get out of here. Okay. So then my number must be 0.0273. So I'm going to do my subtraction here. And I get 0.1227 for nitrogen. For hydrogen, I have to do it 1 minus 3 times this. So I get 0.0681. 0.05 plus 2x equals like 0.1046. Those are my three answers. I will give you 5 extra credit points in class if you bring me this hand solved. Well, y'all are going to cheat on that too. Okay. If you can hand solve it in class next week, I will give you 5 extra credit points. I'm very curious if you can do it. Okay. Let's continue. Last thing. Our last thing we're going to talk about is Le Chatelier's principle. With this little fancy looking A. It's a old rule, and here's kind of the basics, and then we'll kind of explain what it's about. His language, Le Chatelier, when he named it, says, if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction to reduce that change. Okay. Basically what this says, that any system will shift to counteract any change that gets made to it. Okay. A system is going to do its best to neutralize any change. This kind of works like our buffer system in our body. Our buffer system, we learn all about buffers next unit, just wait. But our buffer system, if you add too much acid or too much base, it's going to help neutralize that, to help maintain your blood's pH level. Le Chatelier's principle works the same. If you have a reaction that's at equilibrium and you add more reactants, the system will shift to the right to try to reduce that amount of reactant that you added. If you add some extra product to the system at equilibrium, it'll shift to the left to try to reduce that new product being added. A system's going to try to counteract any change you made to reduce the effect of it. So first, let's look at concentration. The system will shift away from the added component, or if a component is removed, the opposite effect will occur. So we have here, H2O is removed from this reaction. Get rid of H2O. My system's going to want to try to counteract that change. So it's going to try to replace it with new H2O as you remove it. So it's going to shift to the right. This one, some iodine is added. I'm adding iodine, which is right here. It's going to try to counteract that change and get rid of that iodine. So it's going to shift also. Oh, I got myself. Yeah, it doesn't matter. Iodine is a solid, so there's no change. I should have read ahead. Okay. If I added hydrogen, it would have shifted to the right to counteract it. But solids and liquids just don't matter for this entire unit. Le Chatelier's principle also has an influence with temperature. Now, this is getting a little ahead of ourselves. We haven't quite learned a lot about thermodynamics, but you might remember a little bit from honors chem or something. Enthalpy is a measure of if a reaction is endothermic or exothermic. A positive enthalpy, which has this delta H degree symbol, is if it's a positive number, that means it's an endothermic reaction. In an endothermic reaction, you have to add heat to the reaction to make it happen. So we can think of heat as a reactant. You need the heat to start the reaction. If that delta H, that enthalpy, is negative, the opposite's true. It's producing heat as a product. That's what exothermic means. So we would treat energy as a product and then use that idea to help us determine which way it shifts. Let's look at this example. I have NO2 gas, oxygen gas, NO gas. All of them gases, so they're all there. I have an H plus that is positive. My enthalpy is positive. Okay. Let's talk about how I would work this out then. NO2 plus O2, 2NO. Enthalpy, positive 181. Doesn't even matter, but the fact that it's positive does. You can think about this. You need this much heat to start the reaction. So when I rewrite it, I'm just literally going to write the word heat on the left side. Heat is just a reactant. If I add heat, if I make the heat go up, the reaction will shift to the right to counteract that. If I reduce the temperature or reduce the heat, the reaction will shift to the left to counteract that. Okay. Oops. Okay. So since this is an endothermic reaction, energy is a reactant. They put the exact number in this PowerPoint. It doesn't matter. Just the word heat works for me. As K increases as temperature is increased, which also means the equilibrium will shift to the right. Okay. If it's a negative number, that just means the opposite, right? That just means a negative enthalpy. Negative enthalpy. It will be a product. So this reaction, 2SO2 plus O2, 2SO3 plus heat. So negative, you put it on the right. Positive, you put it on the left. We'll learn more about what this means specifically. That's all you need to know about it for now. Okay. Just about done. The last thing that Le Chatelier's principle involves is pressure. This one's the most complicated. Increasing the pressure will shift the equilibrium towards the side with fewer moles of gas. If you increase the pressure, it's going to want to reduce the pressure. It's going to want to cancel your changeout. So the reaction is going to shift. There's no pressure as a reactant or product, but it can shift towards the side with less gas. That'll lower the pressure through like the ideal gas law. Decreasing the number of moles of gas decreases the pressure. So increasing the pressure will shift towards the side with more moles of gas. Okay. Opposite's true. Decreasing the pressure is going to shift towards the side with more moles of gas to try to restore that pressure that was lost. Increasing the volume will have the opposite effect. Pressure and volume have an inverse relationship. Making something smaller increases the pressure inside of it. Making something bigger decreases the pressure. So if you increase the volume, it's going to shift towards the side with more moles of gas. Okay? Because increasing the volume decreases the pressure, so it's going to want to get that pressure back up. There's like a whole string of logic we have to try to follow. Decreasing pressure or volume will have the opposite effect. So increasing will do one thing, decreasing does the opposite. Here's a couple of examples we'll talk about. We'll have plenty of these in class. People usually like this, like it's not too bad. Predict the shift in equilibrium when volume is reduced for each of the following reactions. Okay, volume is being reduced for each one. If volume is being reduced, it's shrinking. The number of moles stays constant, so the pressure goes up. So another way to think about volume going down is pressure going up. What happens in each of these when the pressure goes up? It's going to shift towards the side with less moles of gas to counteract that. So in A, the left side has gas, the right side doesn't. Okay? Volume is being reduced, which means pressure is being increased. I have 6 moles of gas on the left, none on the right. I'm going to shift to the right to try to reduce that pressure increase by making less gas. And number 2, I have gas on both sides. The left side, my total number of moles of gas. I'm going to add my coefficients of everything with gas. I have 2 moles of NH3, 3 moles of N2O. I have 5 total moles of gas on the left. On the right side, I only have 4. So I have 4 nitrogens, and the liquids don't matter. If I increase the pressure here, I have more moles of gas on the left than I do on the right. Camera's backwards. Okay. I'm going to shift to the right, towards the side with less moles of gas to try to counteract that increase in pressure. Last one. On the left side, I have 4 moles of gas. On the right side, I have 4 moles of gas. It's no shift going to occur when I change the pressure. It doesn't care which way it goes. I have the same number of moles of gas on each side. Moles of gas are kind of weird. It doesn't matter what the gas is because all the molecules are independent. They can move around the container by themselves. So they don't care which gas you have. Any gas works the same for the math. Last thing here. It's important to realize that changing concentration of products and reactants and pressure changes only affect the equilibrium position. It does not change the equilibrium constant. K is going to be the same number regardless of how much initial stuff you start with. Eventually, equilibrium will be reached. It is inevitable. All right, I think that's the last slide there. All right, a lot of topics to talk about. Things I definitely want you to know. How to write an equilibrium expression. Going into our class talking about this is really important. I'm going to be doing that, setting up a nice table, even if you can't solve them fully. We're going to do a lot of practice on that. Le Chatelier's principle, I kind of breezed by here at the end. That's totally okay. We're going to talk about that a lot. You guys won't have much trouble with that. And last thing that's really important is K and Q. Calculating K, calculating Q, comparing them. if you have at least some understanding of all those things, you'll do fine in class this week. We'll go over some of the math in a little bit more detail. I won't cheat and skip out of it unless you really want me to. And yeah, so I will see you all in class next week. All right, have a good one.